Okay, here's example 6 with integration by parts. So this one's going to be a little bit different from the other 5 we looked at, and we'll see how shortly. But let's just approach this the same way we always do for integration by parts. So what we're going to do is use this Liate or whatever rule here. So remember, integral of u dv equals uv minus the integral of v du. Okay, so here's our integral that we have. This is the integral of u dv. So we want to know which one of these guys is u. Okay, we want to know what do we pick to be our u. So remember, the rule is just go down this list, and whichever function you have that appears first in the list, let u be that function. Okay, so e to the x, that's an exponential function. Cosine of x is a trig function. Trig functions appear higher on the list. Okay, so we're gonna, if we go down from top to bottom, we're gonna hit those first. So we let u be the trig function. Okay, so what I'm gonna do first then. Totally unnecessary, but not a bad idea for the sake of the video, I guess. I'm going to rewrite, so I'm going to swap the terms here, e to the, or the factors, e to the x cosine of x. I'm going to swap that and write cosine x times e to the x. Okay, so why am I doing that? Because now I can just quickly identify, okay, I'm going to pick u to be the trig function, okay, again, because it appears higher in the list, okay? And then since we picked u to be that, dv has to be everything else left over. So that means dv has to be this guy here. Okay, e to the x dx. Remember, dv always has to have a dx on it, or d, whatever the variable is. Okay, in this case, it's just x. Alright, so now we're going to come over here and write what we have. So u equals cosine of x, and dv is e to the x dx. So if u is cosine of x, what's du? Remember, du is just the derivative of u with the dx on it. So the derivative of u, derivative of cosine of x, is negative sine of x. Okay, and then since it's du, we have to have a dx on it. Okay, so du is negative sine of x dx. And then let's zoom in a little bit here. Now if dv is e to the x dx, how do we get v? Well, remember, v is just the integral of this, right? So integrate dv to get v. So if we integrate e to the x dx, we get e to the x. And remember, for integration by parts, forget about the arbitrary constant, okay, at this step here anyway, at this step. Okay, so now what we're going to do is use this formula. Okay, we're going to use the integration by parts formula. So the integral of u dv equals uv minus the integral of v du. Okay, so the integral of u dv equals uv, which is cosine of x times e to the x. So this equals cosine of x times e to the x minus the integral of v du. Okay, of v du. And v du is e to the x, okay, that's v. So e to the x times, what's du? Negative sine of x dx. So this is going to be negative sine of x dx. Okay? So that's what we got going on over here. So now let's simplify this a little bit. So let's actually do this. Let's write this. So what we have so far is the integral of e to the x cosine of x dx equals, I'm going to write this as e to the x cosine of x. And then here minus negative becomes plus. And then we have integral of e to the x sine of x dx. Okay? So, so we started with integral of e to the x cosine of x, and then we did integration by parts. Okay, just a standard integration by parts, nothing different yet. And then we ended up with this integral here, integral of e to the x sine of x. So it sounds pretty similar, right? It sounds pretty similar to that, and it is. So what we're going to do now is integration by parts again on this guy. Okay, so what do we have? We have another exponential function and a trig function. So if we follow this Liate rule, how do we pick our u? Well, we start at the top of the list, work our way down. First thing that appears is trig function, so we let u be that again. And now, also I want to point out, we talked about it in an earlier video, so I don't want to spend too much time talking about it again. But we already used u and v here, so we really shouldn't use them again. It's bad math etiquette, sort of impolite mathematically. So instead of u and v, let's use w and z. Okay, so then the integration by parts formula is going to be integral of w dz, okay, w dz equals, the integral of that equals wz minus the integral of z dw. Okay. Okay, so again, why are we doing that? Because we already used u and v, so we really shouldn't use them again. Most instructors might not care, but it's, yours might, so be careful about that. But also, it's really a bad habit to get into, reusing variables like that. It could be kind of dangerous and tricky. Could lead to some problems later on. And for this particular problem example, it won't be that bad, but it's just, in general, it's good to avoid getting into that habit. Okay, so anyway, now we're going to tackle this one with integration by parts using w and z. Okay, and like we mentioned in the other video where we did this, it's good to do this with different variable names so that you can get used to the idea that it doesn't matter what you call them. Okay, we call them u and v or w and z. It doesn't matter at all what we call them. Okay, it's just a name. The math behind it's all the same. Okay, so now what we're going to do is integrate e to the x sine of x dx. Okay, so now we're going to do integration by parts on that. And again, we're doing w and z. Okay, so w. Okay, so remember, w, that's the place of our u now. So how do we pick our w? Well, we kind of already talked about it. We have a trig function and an exponential function. So if we want to pick our w, which is our new u, okay, w now, go down the list from top to bottom. What appears first? Trig functions appear first. So we let w be sine of x. Okay? So w equals sine of x. So that means dz has to be everything else that's left over. Okay, so what I want to do now actually is write this like this. So this is going to be integral of sine of x times e to the x dx. Okay, why did I do that? Because now I can easily identify, here's w, okay, so then dz, okay, dz now has to be everything that's left over. Okay, so w is sine of x, dz is e to the x dx, dw, okay, if w is sine of x, then dw is the derivative of that with the dx on it, so the derivative of sine of x is cosine of x. And then slap on a dx. Okay, cosine of x dx, that's dw, and then z, what's z? Okay, well, just like up here, okay, the math is exactly the same, we're doing integration by parts, but we're just calling them different things. Okay, up here we used u and v, now we're doing w and z, but the math is exactly the same. How do we get z from dz? Just integrate. Just like when we wanted v from dv, we integrated, okay? Well, it's actually the same thing here. So integrate e to the x dx, forget the arbitrary constant for this step, and you just get e to the x. Okay. Okay. So now we come over here. What do we got? We have this equals the integral of wz. Okay, so wz. The integral of w dz equals wz, which is sine of x times e to the x. Sine of x times e to the x, minus the integral of z dw. Okay, z is e to the x, dw is cosine of x dx. Okay, so kind of feels like we went in circles a little bit, right? Because what do we start with? We started with the integral of e to the x cosine of x. What do we have here? The integral of e to the x cosine of x dx, right? So now this next part, it's not really complicated. It might be a little bit tricky because this is something sort of new. You might not have done this in a calculus course before, but it's really not that bad. And there are certain types of problems that require this sort of thing here. But now what we're going to do is let's combine all the results into one. Okay, so what do we have? Let's combine everything here. Okay, so what we had at the beginning was integral. Okay, so let's set off some room up here. Whoops. So anyway, what we had was integral of e to the x cosine of x dx. Okay, that's what we had up here. Integral of e to the x cosine of x dx equals e to the x cosine of x plus the integral of e to the x sine of x. Okay, this is what we got from our first integration by parts. Okay, when we did integration by parts the first time, this is what we ended up with. Okay. Plus integral of e to the x sine of x dx. Okay. But then we did integration by parts on this guy, and we found out that this integral right here, okay, this integral right here equals this whole thing here. Okay. So now let's take this. Okay, so remember we did integration by parts on this. That's when we did integration by parts the second time. We did it here, and we found out this integral equals this expression here. So let's take this expression and stick it into this equation here. Okay, so then we have this integral of e to the x cosine of x dx equals e to the x cosine of x plus, okay, remember this entire expression equals this integral, so this is going to be, I want to write this as e to the x sine of x because it's more standard, I guess. E to the x sine of x, and then minus the integral of e to the x cosine of x dx. Okay, so now let's make that a little neater, easier to read. So what do we do now? It looks like we might be kind of stuck, but actually the rest of this is fairly straightforward, well, maybe not straightforward right away, but it's fairly simple. So what do we have here? Big ol' integral equals e to the x cosine of x plus e to the x sine of x minus the same big ol' integral, right? So seems kind of strange, right? But let's forget about this integral here. What if we had something like this? What if I were to say to you y equals e to the x cosine of x plus e to the x sine of x minus y. Okay, what if I were to give you that equation and ask you to solve for y? Solve for y in terms of x. What would you do? You would add y to both sides, right? And then you'd get 2y equals e to the x cosine of x plus e to the x sine of x. And then you divide both sides by 2, right? Okay. Why did I go through this here? What's the point I'm trying to make? Well, the point I'm trying to make is, here's a big ol' y, big ol' y. It's the exact same idea over here. Integral of e to the x cosine of x dx, blah, 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 minus integral of e to the x cosine of x dx. Okay? So it's the exact same idea as up here. Okay, you have just y, and then blah, 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 minus y. Okay, so they're the exact same things, just this one here, and then this minus the same thing over here. This integral here minus the same integral over here, right? So we would just solve this equation the exact same way. Okay, so in other words, what we do here with the thing I just erased, we add y to both sides, divide by 2. Here we're going to add this integral to both sides, okay, and divide everything by 2. Okay, so let's come up here and do that. So I'm kind of running out of room. So what we want to do then is add integral of e to the x cosine of x dx to both sides of this equation. Okay, e to the x cosine of x dx. Okay, so when we add this integral to both sides of the equation, what's going to happen? What we're going to get is 2 times the integral. Okay, so on the left-hand side we get 2 times this integral, 2 times the integral of e to the x cosine of x dx equals, what happens over here? Well, we still have e to the x cosine of x plus e to the x sine of x. Plus e to the x sine of x. And then what happened here, minus e to the x, minus integral of e to the x cosine of x plus integral of e to the x cosine of x dx. Okay, so these kind of cancel each other out. So these are gone. That's great because now what we can do is divide both sides by 2, and then we end up with integral of e to the x cosine of x dx equals 1/2 times e to the x cosine of x plus e to the x sine of x. Okay, and then that's almost, so let me zoom in a little bit on that. Let's make that a little bit easier to read. Okay, so all we did here was just divide both sides of this equation by 2. And there are a few different ways to write that. You can distribute the 1/2 if you want. You can put all of that over 2, like with the big old fraction bar. Whatever, doesn't matter. Okay. Now there's one tiny little thing left to do. What is it? This is an indefinite integral, right? So we got to have a plus c. Okay, that's very easy to forget that here because it doesn't really come out naturally. You know, when you do integration by parts, usually you just end up with something where you could just tack on a plus c at the end. But you want to be, well, this is kind of what we have here, but since we're doing something different, it doesn't really feel natural, so to speak. And it's kind of tricky a little bit and it's difficult to remember we have to tack on a plus c. But just remember, indefinite integrals, they got to have an arbitrary constant on the end, or at the end of the problem anyway. So the integral of e to the x cosine of x dx is 1/2 times e to the x cosine of x plus e to the x sine of x, and then tack on arbitrary constant plus c. Okay? So let's recap what we did real quick, and I want to make a note of something. Okay, so what do? we had the integral of e to the x cosine of x dx. We did integration by parts on that. And when we did integration by parts, we ended up with the integral of e to the x sine of x dx. We did integration by parts on that, and then we ended up with this expression here, where we had blah, 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 minus the integral we started with, okay? So then what we did is we put everything together. So integral of e to the x cosine of x dx equals e to the x cosine of x, okay? E to the x cosine of x, plus this integral here. Well, remember this integral we did it with integration by parts, and we got this expression here. Okay, so we took this expression, stuck it into this equation here. Okay, so that's where this came from here. Okay, this expression is the same as this expression, which we know is equal to this integral, because that's when we did integration by parts the second time, that's what we found out. Okay, so then putting it all together, we have integral of e to the x cosine of x dx, the thing we started with, equals this e to the x cosine of x, which came from up here, remember, plus that integral, which is e to the x sine of x, minus that integral we started with. Okay, so here's a thing equals some stuff minus that same thing. Okay, so we want to solve for the thing. Okay, so again, thing equals blah, 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 minus that same thing. So just add that thing to both sides, so then we get 2 times that thing, okay, equals blah, 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 and then divide both sides by 2, so we just have that thing equals all this mess here. And then don't forget the plus c because it's indefinite, okay? So that's pretty much how you do this one here. So it feels kind of like you're going in circles a little bit. And you do want to be careful because it's easy to make some mistakes here and there that could send you going back into circles. But there's a couple things I want to point out here. First of all, this is the integral of e to the x cosine of x dx. What if you started with the integral of e to the x times sine of x dx? If you started with this integral, it would be exactly the same process, literally exactly the same. Just your u's and v's, well the u's anyway would be a little bit different, because here you would first choose u to be sine of x, and then dv would be e to the x dx. But you do it exactly the same way. Do integration by parts twice, you end up with blah 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 equal, or you end up with a thing equals blah 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 minus that same thing. So you add the thing to both sides, and then you divide by 2. So the process is identical. Okay, the functions and the steps along the way they'll be a little bit different, but the process is literally identical. Okay, that's one thing I wanted to point out. Another thing is we follow this Liate rule here, which you always should for integration by parts, but I want to point out, just FYI, that for this specific example and also for the e to the x sine of x, if we do that one instead, it actually doesn't matter which one of these you choose to be u. Okay, so if we follow this rule, we should choose u to be the trig function. We did, that's good. But actually, if you choose u to be e to the x, then dv is cosine of x dx. This will still work, okay? But I want to point something out here that's you got to be very careful if you do that, because if you choose u to be the exponential function here, then you have to choose u to be the exponential function in the second time you do integration by parts. Okay, so here we chose u to be the trig function, and then in the second integration by parts we chose our u, or w I guess in that case, to be the trig function again. Okay, so but again we could have chosen u to be the exponential function here and w to be the exponential function here. That would have worked out. Okay, but it's best just to follow this Liate rule. So that's just for this specific example. It would not have actually mattered. So that's just a nice happy little coincidence. But it's always best to just follow this. So just go down the list, whichever one appears first, choose that to be your u, or whatever you're calling the variable. Okay, u or w or whatever. And one thing I want to point out with that, why is it tricky? Why do we have to be careful? Well, if we chose u to be the trig function here, and if we chose w to be the exponential function here, so if we kind of mixed them up like that, then what would happen here, the second time, we would just kind of undo what we did with the first integration by parts, and we'd kind of be back to where we started, and we wouldn't have anything that helps us out. Okay, so that's why we want to be consistent and just always follow this. So even though it will work if we choose u to be the other function in this case, we want to be careful, because if we mix them up like that, like if we choose u to be the exponential here and the trig here, or if we do the trig here and the exponential here, it's going to kind of mix up and undo each other and then cause problems for us. So that's why it's really always best to just follow this rule here when you do integration by parts. Okay, so just some things I want to point out there. Okay, so that's example 6 with integration by parts, a little bit different, but same idea, just integration by parts, follow this rule here for choosing u. And then the only difference here was we did integration by parts twice, and then we had this different step here where we had to add this integral to both sides, end up with this, divide by 2, and then don't forget to tack on a plus c. Okay? So that's example 6 with integration by parts.